Hello everyone, I am Darius Coelho and I will be presenting our work on designing a visual and contextual nutrition facts label. This work was conducted by myself, two talented high school students Helen Hay and Maxine Badu, and my advisor Klaus Mueller. So let's start off by taking a look at the current nutrition label design. This is an example of a nutrition label design as specified by the US Food and Drug Administration or FDA. It is a textual label that uses font styling such as font size and making text bold to emphasize important nutritional content of a food product. However, recent studies show that it is still difficult for a large number of consumers to understand and make comparisons between food products. They often make errors when computing and estimating the contribution of food's nutritional content to their daily nutrient requirement. They also find it difficult to compare food products with this label. We attempt to overcome some of these limitations by designing a nutritional label that makes use of a visual representation to communicate nutritional information. Specifically, we aim to clearly communicate the level or quantity of a nutrient in a food product, as well as indicate where this quantity is placed within the range of quantities of this nutrient in similar products. For example, when considering the amount of sugar in drinks on a scale of water to Coca-Cola, we would place juice closer to Coca-Cola. Thus, our visual label must be designed to show exact values of nutrients within a reference range. It should be compact enough to fit onto food products and should have some level of similarity to the current design so as to fit into FDA regulations as well as minimize the learning curve for viewers. To accomplish this, we base our design on the bullet chart developed by Stephen Few, shown here. It has a small footprint and is based on bar charts. It also has some resemblance to progress bars, which we believe would make it easily understandable to the general public. I will explain our modified design with an example. Consider we are looking at the product spinach and feta chicken and turkey sausage. According to the FDA's database, it falls under the sausage category, which in turn is in the sausage and luncheon meat food group. We represent each nutrient with a single modified bullet chart, such as this. Here we show the protein content of the sausage. The extent of the entire range is the required daily value for an average adult on the 2000 calorie diet. The light blue bar represents the range of protein content across items in the sausage and luncheon meat food group. Similarly, the darker blue bar represents the range of protein content across items in the sausage category. And the level of protein in the current food, spinach and feta chicken and turkey sausage, is shown with a black marker. We also report the level of the nutrient in terms of the percentage of daily requirement. In this case, it fulfills 30.6% of the daily requirement. Now, with this design, we can easily see that the food contains 15.3 grams of protein, which fulfills 30.6% of the daily required value. We can also see that this food is close to the middle of the protein range of foods in the sausage category or in the sausages and luncheon meat group. With this information, the viewer now knows that he or she can opt for an alternative but similar food if their protein requirement is higher or lower. If a range of value goes beyond the daily requirement, we indicate this by adding an arrowhead to the end of the range. It should be noted that we also follow the FDA font and unit guidelines when labeling the bullet graph. Foods contain multiple nutrients, each of which we represent with a bullet graph. However, there is a limited amount of real estate on food packages. Thus, we consider two layouts. First is a linear layout, where the bullet charts are laid out sequentially from top to bottom and follow the sequence specified by the FDA. The second is a radial layout that arranges the bullet charts in a clockwise manner following the sequence specified by the FDA. The linear layout bears close similarity to the standard label in terms of design. It is essentially the same label, with an additional column in the middle containing the modified bullet charts. The design of the radial layout, on the other hand, deviates significantly from that of the standard label. However, we chose to include this layout as it has the ability to save space as the number of nutrients increase. But we do believe that it will be harder to read. In addition to considering two layouts, we consider two unit encodings. The first is a standard continuous encoding, where the range of the nutrient values is represented as a continuous bar, while the second is a discrete encoding, where each bar is divided into 10 individual segments, each representing 10% of the range. We expect that the discrete encoding will help users to easily approximate the quantity of a nutrient and compare values. Having designed different visual labels, We conducted two pilot studies to test which layout users prefer and which unit encoding is more effective. We start with a layout preference. We tested both the linear and radial layout. We added additional variation of each that primarily differed in label positioning and coloring, and we add the standard label to the test. For the study, we recruited 20 participants who were students on our campus. Each participant received a brief explanation of the labels, after which they were asked to rank them based on which they prefer to use when reading nutritional content or foods. It should be noted that we used grayscale versions of the labels so as to avoid engaging users with the color. We used the rankings generated by the participants and computed a rank score for each label. Higher rank scores indicate higher preference. Here we found that participants preferred the linear designs over the standard design. However, the radial designs were the least preferred. This is in line with previous studies that show that radial layouts are generally not preferred. Next, we tested the unit encoding performance. We test a linear layout with the continuous encoding, a linear layout with the discrete encoding, and a standard label. For this study, we recruited 15 participants via social media. Each participant only used one of the three label types to answer 13 questions about a food label. These questions tested the user's ability to read values and ranges and compare values and ranges. Each participant evaluated two randomly selected food products. The results showed that when it comes to reading values, the visual labels perform significantly better than the standard label. However, the difference between the two encoding types was marginal. But when comparing values, the continuous encoding performed significantly better than the discrete encoding, and both outperformed the standard label. When reading ranges again, the difference between the two encoding types was marginal. This was also the case when comparing ranges. To summarize, we designed variations of a visual food label based on the bullet chart. We conducted pilot studies that showed users preferred our linear layout visual label. However, there were no significant differences between the two types of unit encodings. While our studies demonstrate the potential of visual food labels, further testing on a large diverse set of participants is required. Thank you.